All right, today is Variational Quantum Eigensolver Day, or VQE. This is perhaps the most famous variational quantum algorithm, similar to in popularity to QAOA, but I believe the original VQE paper has been cited now more than 1,000 times, whereas the original QAOA paper was only cited 700 times, and I think they both came out in 2014. But either way, both very important. But thankfully, I think VQE is a lot easier to understand and to format. So first, we know that it's important. I talked about this actually in some of the basic quantum computing discussions, but we know the classic eigenvalue problem, which is basically for any sort of matrix or operator A, we want to find the eigenvalues, often denoted lambda, and because the VQE is often used in a applied to some sort of quantum chemistry or some sort of quantum mechanical setup, we will often see something like now, if you've ever taken a quantum mechanics class, this will be all too familiar with you. We can see that the eigenvalues of the Hamiltonian of a quantum system are the energies, the energy levels of that system. And so this Hamiltonian could be anything. Could be, for example, if we have a qubit here or a single state here as our wave function, this could just be the Pauli Z operator. It could be, or it could be the Hamiltonian for the infinite square well. There's a lot of things that this Hamiltonian could be, but it can be represented as some sort of matrix. So that's just what I'm doing here. And so when we have this matrix, we know a couple things. One, we know that the Hamiltonian has eigenvalues. And in order to calculate this, we know that when you measure or when you operate with some sort of operator, you get back an eigenvalue of this operator. And so whenever a measurement in a quantum mechanical setting is just the application of an operator. And so if you're measuring in the z direction, then you're applying the z operator. And so we're getting eigenvalues of this Hamiltonian every time we measure. And so measurements in quantum mechanics, we know that the expectation value of a measurement is defined by this equation here. And this is oftentimes, this is the direct notation of it, but you'll often see it, for example, if you have like the infinite square well, you'll see this in integral form, where it can be, well, this is, well, what this directly translates to is usually dx if these are functions of x. And so you might see this in the infinite square well, where it's the length of the well, and then it's square root of 2 over L sine n pi x over L. And so then you can have this this would be an example of this expectation value from a classical quantum mechanics perspective. This operation could be, if we're trying to find the expectation value of the particle in the box, this could be the x operator, which is just x, or it could be the momentum operator, which is, I hope this is correct. It might be h bar over I don't fully remember. But either way, this is a very established concept within quantum mechanics, is this expectation value. But if we look at this from a linear algebra point of view, we know that this expectation value is going to yield an eigenvalue of this operation. And so we know by definition, if it yields an eigenvalue, then we can also say that it's greater than or equal to the smallest eigenvalue. So we can say, okay, this is definitionally greater than or equal to the smallest eigenvalue, because if you measure it and it is the smallest eigenvalue, it's equal to it, or it's going to be some larger eigenvalue. And so then we can, this is a useful problem in a number of ways. The lowest eigenvalue of some sort of Hamiltonian describing a system is the ground state energy, which has a lot of applications in physics and chemistry and all sorts of stuff. And so this is a worthwhile thing to know. So we can therefore conclude that if we can, set up this operation to minimize this, if we minimize this quantity, we can get the ground state energy. And so, we have this defined Hamiltonian. So what we can do is we can set up these wave functions, or set up the initial wave function, such that when you do the Hamiltonian and then measure and get the expectation value, although you wouldn't actually get the expectation value, you get a value, which you would do many, many times, and then you would get the expectation value. If we can set up these wave functions to minimize it, then we can get the ground state energy. And so this is the general framework of the variational quantum eigensolver. And this is well established. I'll put lots of references. This specific example that I'm going to be doing later comes from a blog post from a researcher, and so I'll be sure to link all that stuff in the description. It's just all of this, information is sort of widely distributed, and it's variational quantum eigensolver has a lot of information, so I'm not gonna beat it to death in terms of the explanations, because really what this is about is doing this in Tensorflow-Quantum. And so now that we know this, we can sort of see the general approach. We set up the wave function. We apply, or I should say, measure using the Hamiltonian operator and get a value. Maybe this might be done many times if you're sampling it. And 3, update, or I should say /min h. And so what this really means is this wave function here is parametrized. So we might have some parametrized gates here that we can then update to minimize this. And so that's the basic setup of the eigenvalue or variational quantum eigensolver. And that's pretty much it. That's all you really have to know. We'll get into a little bit of the details. First of all, normally when you measure in certain simulators, you'll just get 0 or 1 or something like that. But once again, Tensorflow-Quantum is really nice in that you'll see a lot of discussions online if you read about variational quantum eigensolver about having to convert the measurements from like 1 to -1 and 0 to 1. However, Tensorflow-Quantum reads out including negative numbers, and so you don't have to do that. So now we just have to figure out specifically, what does this Hamiltonian look like? And one thing that I want to talk about that I'll get to with the code is the role of readout operators here. And so, yeah, but for now, we're just going to be talking about exactly how to set this problem up from a little bit of a theoretical linear algebra problems, then just implement it in TFQ. Okay, let's get right into constructing a relevant Hamiltonian. So in this case, in this video, since I don't want to make this a super long video, I'll break it into 2 parts. We're just going to be looking at single qubit Hamiltonians. So that's not as realistic necessarily, but I will get into how to do multi-qubit Hamiltonians because it's a little bit different. So first, let's think about any sort of Hamiltonian here for single qubits can be constructed in this form. You can break it down into summations of specific, I should actually do alpha times I plus E times X plus C times Y plus ABCD E times Z. So this is the general form of the Hamiltonian. Any matrix that you could conceive of that's a one qubit matrix, so a 2x2 matrix, can be represented in this form. That's just an established ground rule. So any sort of system we could imagine could be represented in this form. In this case, it's a pretty simple system. Once again, I'm just taking this exact matrix from a blog that I'll link in the comments. And so specifically, what we'll be considering here is the following. I should clarify, C equals 0. Oh, that's also D. I guess I don't know my alphabet. And so if we do this, we can see it's the identity matrix plus the X matrix, which is, see if I know my matrices here, plus 2 times the Z matrix, which is this, which comes out to be 1, 1, 1, 1 plus 2, 0, 0, negative 2, which will be 3, 1, 1, negative 1, 1, negative 1. And so that's the matrix that we are going to find the eigenvalues of. And so before we get off to implementing this, it's worth noting that you can just solve this easily. Like, this isn't a hard problem to solve classically for this simple case. We can just solve this real quick. If you remember how to solve it by hand, you subtract, you do the matrix minus the lambda times I equals 0. So you get the characteristic polynomial of lambda squared minus 2 lambda minus 4. So we see that lambda equals 1 plus or minus square root of 5. And so the minimum here is going to be 1 minus square root of 5, which in its exact form is equal to approximately negative 1.236. And so that's the optimal value, basically. And so we can see this is easy, not even to solve with a computer, but just to solve by hand. But that's not really the point here. The point is more just, showing how to do it in TFQ, which we will now get to when I show the code. So yes, first thing we can see when we're going through the code is that there's two, I'm going to go through 2 examples of code here. One of them that really utilizes the strength of TFQ. So first of all, we have the traditional imports, TensorFlow, Circ, NumPy. Something different that you'll see here is the SciPy optimize, minimize function. This is a pretty common technique because you won't notice it in the 1 or 2 qubit examples, but with growing numbers of qubits, the optimization techniques for gradient descent, theoretically, well, I shouldn't say theoretically, it's been said in literature that they reach a local minimum too quickly, and therefore aren't the best way to optimize them, the parameters of this. So I'll use it here because it does work, and it works in the two qubit case, and it's worked in every case I've actually tried. But a lot of the literature recommends using different optimization methods, such as it doesn't even really matter in this case. Nelder-Mead is the go-to sort of which is just some simplex-based, really famous optimization method. I couldn't write the code for it, but it doesn't matter because it's implemented here. And so the first thing that we want to do is I have the code written here for a general framework for any sort of single qubit Hamiltonian. So normally what you would do is you would construct a separate sort of circuit, a separate entity for each part of the Hamiltonian, and then sum them up. And so, if this is physically implemented on hardware, it'd be a lot different. However, I just choose to do this all as one circuit. Specifically, I just use X, Y, and Z operators, even when, they're like in the example I'm providing, we don't use Y at all. So this is the classical way that you'll often see it in literature, but depending on your needs, it might be easier to implement in a certain other way. So first, let's consider there's 3 qubits because there's the 3 possible X, Y, or Z combinations. You'll notice, not in this video, but next time when I do the 2 qubit case, that I hard code actually the circuit. I mean, I shouldn't say hard code, that sounds bad, but I designed the circuit specifically because the number of combinations is a lot bigger, because you could have X, Y, or Z on either of the 2 qubits, or ZX, XZ, YX, ZX. Like, there's all sorts of combinations that just grow huge and unsimulatable. So you want to specifically narrow it down. And if you're simulating really large sort of Hamiltonians, for example, if you have a 10 qubit Hamiltonian, so it's a sum of 10 qubit Hamiltonians, you will want to write them separately, because if it's like 10 terms of each with 10 qubits, you can't simulate 100 qubits, so you're going to need to write them separately and then sum them, which is completely doable. It's just not how I wrote the code. Maybe I can write a even bigger example for next time that does show that. So the first thing we want to do is note that an important aspect of this is that the parameter that you use for the wave function, or for the initial setup, is shared across these different qubits, because this is supposed to be like the same circuit, right? You're thinking of it like you're just summing up these terms, but the setup of these terms should be the same. Because if I go back real quick just to really emphasize this point, if this is a wave function parametrized by theta, and you're computing the expectation value of the Hamiltonian, and so this is equal to, remember, maybe it's in this case it's the ZX, so this is the Z X. So this is basically what we're doing, plus the identity. If the parameters are not shared across layers, then this wave function is different from this one, and so you're computing something just entirely different. It's important to recognize that because this is the original formula, we're breaking the Hamiltonian down into a sum of parts, which is then parametrized for each operator. So keep in mind that you can't, you could get a lot lower, I guarantee it, if you had different parameters. But that's just an important note to be aware of, is that the parameters are shared across these different instantiations. So now let me Alt tab over, and we can see that in this case there's just one parameter. So now we create the initial setup, and so we can see here that we apply the parametrized RY gate to each qubit. And then qubit 0 is the X part of the Hamiltonian, qubit 2, or qubit 1, sorry, starting from 0. Qubit 1 is the Y part of the Hamiltonian, and qubit 2 is the Z part of the Hamiltonian. And you see these here because typically when you see variational quantum eigensolvers, everything is measured in the computational basis, or the Z basis. So we therefore need to convert this, if we're measuring the Hamiltonian and you just measure the Z basis, That's not what we want. We want the x basis. But if you're measuring in the z basis, to get the x basis, you need to first rotate y -2 pi, or for y, you need to rotate x pi over 2, which I'm pretty sure is equivalent to Hadamard z Hadamard or something like that. You'll also see that occasionally. So that's what this form is, and in this version, this other version, I'll show later, you'll see the power of TFQ if you can measure in different bases directly, which is important. I don't know from a hardware perspective. I have no idea how feasible that is. I really actually don't know anything about measurements on hardware, so you might want to avoid that if you're doing realistic research for hardware, or you might not. Who knows? I'm sure someone knows, but I don't know how feasible that is on hardware. So now we create the circuit. And so this is really simple, right? There's 3 qubits, one for each part of the Hamiltonian, parametrized and then adjusted for the output. Notice that the second qubit, or qubit 2, starting arrays on zeros is messing me up here. Qubit number 2 has no adjustments because that is the z qubit. And so now we have the readout operators, and here, no matter what, we see a strength of TFQ is it's really easy to make this all built in. So this layer has a single output. You don't have to, I've seen examples in like Penny Lane and stuff where you have to do, fancy work to read out from the circuit, then deal with after the circuit's been analyzed. You have to do all this stuff. No, it's right. TFQ makes this easy to just directly read out from this model exactly what you want. So you compute this Hamiltonian. So it's in the form of the identity, which is just a constant at the beginning, and then these constants times, and we're reading out in the computational basis because that's standard, as you can see here. And then you sum over all of these because remember, we're breaking down a Hamiltonian into a sum of these parts. And then we construct, this should be all too familiar by now. Input of strings, initialization is random. I'll get to these two differences. The two differences here I'm going to show is that one of them is actually sampled. One of them, which is more realistic than the intricate knowledge that this one reveals of the expectation value, which we don't usually have direct access to in a real model. Then we construct it. We use mean average error, pretty standard atom optimizer. Notice here I do central difference for computing gradients just because it's fast, and I don't want to use parameter shift because that would take a while. And then we have 1,000 epochs of gradient optimization. I could set this to be -1,000. It doesn't really, it matters for optimizing, but as long as it's just below what you want, it'll optimize to be it. Then we print a loss function, and we show the trainable variables and what it thinks the lowest value is. Notice that the input here is just a blank circuit, nothing to it, no pre-setup. And so if we just do this exactly here, we can see, oops, well, spoiler alert there. We can see that, what did I call this file? Single.py. Oh, I misspelled single. Classic. That's pretty funny. So we can run this, and I'll actually stop it before it gets to gradient descent part, just to highlight what the circuit looks like. So we wait for it to load. There we go. I'm going to cancel it before it does anything, just for 1 second. So we can see this is the readout operator. It does all the math for us. This is what the circuit looks like. So this is the X part of the Hamiltonian, the Y part of the Hamiltonian, and the Z part of the Hamiltonian, parametrized by the same parameter. Note too that this is not one circuit conceptually. These are meant to be different sort of aspects of the Hamiltonian that are then summed up. So if you have, if your Hamiltonian has 8 qubits, and then you're breaking it down into 8 qubit parts, this wouldn't be, you wouldn't all run them simultaneously on the same circuit. This is just an example of how to do it easily in TFQ. And so now we can actually run it this time with the gradient descent. It shouldn't take that long. We can see there's a single parameter and it's a tiny circuit, so it goes pretty quickly. And then I'll show how to use SciPy minimize, and I will talk about the sampling, and then that'll be all. You can see if I were to do also talk about the multi-qubit Hamiltonian, that would take absolutely forever. And so I'm going to break that up next time. We'll talk about the multi-qubit Hamiltonians, but for now, let's see if it actually reaches its minimum. I don't know if it's going to in 1,000 iterations. Because it's randomly initialized, there is always that, chance it doesn't make it. It looks like it's going to be good, or at least very close. Pretty sure the optimal is about 0.76. So we can see what the loss function looks like if I just add it. Share this window capture real quick. You can see loss function looks pretty good. Now I can hide that. Yep. And now, oopsies. And now we can see down here, this is the parameter. So it thinks the optimal parameter is a little more than pi. And the optimal value, it says, is negative 1.233, which is very close to the optimal negative 1.236, which is what we analytically calculated it to be. And so we can go back now to the code, and we can do two things. First, because gradient descent also takes a while in terms of convergence speed, I could adjust the learning rate, but I'm not going to do that. Rather, I'm going to use the SciPy minimize, and we can see here that SciPy minimize takes a function, a method, and an initial guess, and it minimizes it. And so we have to write this circuit as a function of the weights. And so this is easy. We just set the weights to the values, we get the input, and then we return the NumPy version. And so, what we can see is it'll print out a nice, pretty summarization of the optimization of the optimal values, convergence times, etc. And then this is actually small enough that we can just also do a line space and just look at how changing the value actually affects the output. So if I go back to these and rerun this will be a lot quicker in terms of convergence. And this is you can use different methods. In this case, this is the Nelder-Mead, which is pretty standard. I'm pretty sure that's what they use in the original paper as well. So this is what it prints out. You can see this is the final function value. You can see it actually converges to a better function value too. Although if I had left this training more, it might have converged. It converges to what I think is the exact optimal, basically, eigenvalue. It terminated successfully. I don't know exactly what these mean. I assume it just means how many calls it made. And this is the optimal value. And now we can see, I will share the where is it? Where is I have to share the figure of what it looks like. I'm trying to find, nope, in my mechanism for sharing my screen, I'm just trying to find the okay, I'm gonna pause real quick. Okay, there we go. I was able to find the where it was in my thousands of things I have open. But we can see here, this is what the energy looks like as a function of the parameter. We can see the minimum right down here, and that's what we're converging to. And so you can see it's pretty smooth, which is what we're going for. And so that's pretty much it. However, one more thing that I want to talk about is this sampling. So in the real world, well, what I think usually they do in the real world is that you do not know the exact state of everything in your system, hence why you're doing it. Rather, you have to sample. And so now we can see here, each time we are sampling 64 times. And so we're getting some sort of average, some sort of estimation of the expectation value. And so if we do this, we can see what I'm trying to highlight here is that it will not be as good of a convergence because 64 is oftentimes not enough. And so we'll see momentarily when it converges exactly what I'm talking about. And then, so let's wait for it to converge. Yeah, so we can see here it thinks the minimum is 0, which is not what the minimum is at all. And we can see part of the reason that it's so bad, even worse than when I'll show the line search, even worse than that is because it's adjusting the algorithms, adjusting to what it sees. And so if it sees something bad or confusing, due to chance, it moves in a wrong direction. And so you can see it didn't even converge on a solution because of the probabilistic nature of measurements. You can see maximum number of function evaluations has been exceeded. I don't know what the maximum is. I assume that's a setting I could change. But now if we look at the window, let me add this in, we can see how jagged it is. You can see if we did this method, we would reach a much better solution. But you can see how jagged it is because it's an average based off of only 64 estimates. You want a lot better than that. So now if I go back and I were to change this, I won't share it, but I'm changing the repetitions to 1,000 samples now, rerunning it, we should see a lot better results. And this is really what happens usually on hardware is you have to sample it many, many times, but that's okay because it's really, really fast. Even deep circuits aren't usually that slow. We can see here it reaches a value that you can see it's incorrect. It's actually below what the lowest value should be because it's sampled probabilistically, and so it's just a result of that. But you can see if I share the window or the nice little diagram, we can see that it looks a lot smoother. And so basically that is how you do VQE and TensorFlow-Quantum. One last thing I want to talk about is fully utilizing TensorFlow-Quantum. You'll see this is very standard, doing these operations to adjust for the z basis. But the nice thing about TensorFlow-Quantum is you don't need to read out in the z basis. You can read out in anything you like. Actually, I think it has to be, there's a subset of operators you can read out in. I don't think they yet allow for custom operators. And so if I change this to be, rather than adjusting the Hamiltonian for the z basis, I can just read out in the x, y, z basis. Then I can optimize it, and you'll see if I run this code, it'll converge. This is the expectation value code, so it'll converge exactly to the exact same solution. I forgot to, there we go. I'm running the code right now, and it'll converge to the same solution. And so you can see it's a lot simpler of a circuit, and we're reading out in different bases. And so basically, this is a very fancy way to find eigenvalues of a matrix. And why this matters is because the matrix Hamiltonian can be for a system that's hard to solve classically. For example, if you have, this is a 1 qubit system, you could think of it as, because it's multiple 1 qubit systems. But you could consider if you had a 10 qubit system, maybe your Hamiltonian is 10 different 10 qubit systems, and you have your you're capable of representing a Hamiltonian of 2 to the 10th or 1024 by 1024 matrix. And so very quickly, that gets really hard to solve classically. And so you can see why this is an important problem. And so, but it's a lot simpler than QAOA. I just went into more detail here, and we can see now that the VQE has been solved using TensorFlow-Quantum. And so, yeah, like I said, a lot of this was based on a particular researcher's blog post, which I will also link, and all the code will be available. You can try out different things. And I also have already written the code and run the experiments for not only running a multi-qubit Hamiltonian, but also replicating an exact paper that found ground state energy for hydrogen atoms based off of, or H2, based off of bond length. And so you'll often see the curve, the sort of Leonard Jones-esque curve. You'll see it in probably any intro to sort of chemistry class, or maybe I saw it in quantum physics too. And we'll recreate that using a variational quantum eigensolver. And so you can see there's a lot of potential here. Kept it short, but next time will be multi-qubit VQEs.